So the final exam is going to be on Thursday during class time, exactly the same way we conducted exam 1 and exam 2. Our final exam is also going to be very similar, but there are a few key differences that I want to point out now. The exam length is the same. We are going to use our full class time, 8 to 10:05 Eastern time. But because there's a scanning and uploading step involved here, we are going to take the exam from 8 to 9:45, and then the last 20 minutes of the exam can be reserved for scanning and uploading to Gradescope, just the same way as you guys did in the previous two exams. And so that we have all the information, so your name and page number, please write your name and page number on each page that you use to show your work. Now, if you are printing the exam, then that's okay. That's an option. Some of you have, if you have a printer accessible, if you have access to the printer. But if you don't have access to the printer, then what do? You look at the questions on your screen. You look at your questions on your screen and answer on blank sheets of paper, and then that's what you would write your name and page number on, and that's what you would scan eventually. Once you scan your exam, upload all pages and make sure that you map the pages to problem numbers. I believe all of you have done this many times, and now it's almost a default. You guys do that anyway. Let's see. After submission, please go back and check if the submission went through okay or not. So if you have, say, 10 pages that you uploaded, make sure that they are those 10 pages uploaded, and make sure that there is no duplication. It'll take a minute or so, but make sure that your submission went through okay after you submit. Gradescope submission is going to automatically close at 10:05 a.m. Eastern, so make sure that you turn in your work before that. Now, what is allowed during the exam? I'm making the final exam an open book, open notes exam, but the only reason why I'm making this open book, open notes is because it is comprehensive, and some of you might want to have access to a few key things in the course. Now, personally, I don't think you need more than the midterm 2 resources. The midterm 2 resources included Boolean algebra properties and the next state tables of all the flip-flops, right? So apart from that, I don't think you need anything else. However, if you want to, you have the option. So if it's going to be open book, open notes, but the only limitation is you are going to have to either handwrite the notes or print the notes. So they need to be hard copies. I don't want you guys to use your computer for looking up the notes. You can look up the questions, and we can use the laptop for the proctoring purpose, but please don't use your digital devices for the notes or the book. You are free to write them or print them out. Any questions about this? So this is one of the differences. So I just want to take a minute to see if there are any questions. So we can write our own crib sheet. Yes, you can write your own crib sheet, as many crib sheets as you want. There is no limitation on the amount of crib sheets. The only limitation is that it has to be a physical copy, a hard copy. Can we share crib sheets with other students? Sure. Absolutely. But they are going to have to print them out. Yes, you can. Well, Alex, here is the thing. If you want to share it with the students, share it with me too, right? If you, because I can benefit from your crib sheet. It will give me an idea about what students like to see on the crib sheet. So it'll give me some insight into that. So absolutely share your crib sheets, and if other students want to use that, that's up to them. If I were a student taking an exam, I would prefer to write my own crib sheet, mainly because I'm the one who is going to be accessing the crib sheet during the exam. So I need to know where I wrote what. And in fact, whenever I have written a crib sheet for my exams, it helped me process information. It helped me organize my thoughts. It helped me remember where I wrote which identity. So writing a crib sheet is also a learning experience. But if you want to share with other students and other students want to use some of your crib sheet information, that's absolutely fine by me, as long as they print them out. Other questions? Okay. So apart from the physical copies of open book or open notes, midterm 2 resources will be attached at the end of the exam. So those are the resources that I feel you would need. So if you go and look at your midterm 2 exam, at the end of it, you will find the resources, mainly the next state tables for the flip-flops and the Boolean algebra properties. So those are going to be attached at the end of this exam as well. You're also allowed a non-communicating calculator and writing supplies. Okay. So everything else is, same as before. The only key difference here is open book, open notes, hard copies. Hard copy of open book, open notes. All right. Logistics will continue now, and this is something that you have seen before. Nothing new here. You will be required to join the WebEx meeting 20 or 15 minutes before the start of class time, 7:45 a.m. Use the same link as your regular class lecture link. I've also linked it over here. So when I upload these slides, actually I uploaded them already. So you should have access to this PDF. So if you click on that link in the PDF, it'll take you to the same class that we are using right now to meet. So we are going to use time before 8 a.m. to get set up, make sure everybody has the resources, calculator, writing supplies, and if there are any questions, as you know, I make the exam available a few minutes before start of exam time so that people who have the printer can print the exam out if they want to. You will be asked to keep your camera and microphone on the entire duration of the exam. Just keep it on and then focus on the exam. Please turn off your computer volume so that others do not hear anything that is happening on your end. So mic on, computer volume off. Next, during the exam, if you have any questions, please type that as private questions directly to me, and I will be monitoring the exam the entire time. So I'll be responding to those questions right away. Questions here? Okay. Now, what are the topics? So the next few slides, even though they have the topics, I also want to convey what were probably the most important aspects of the course, and I will also give you guys some hints about what questions you should expect on the exam. So first, let's go through some topics. We started our course with number systems, right? We did number system base conversions. We did signed and unsigned binary arithmetic. We represented signed and unsigned numbers as integers, also as fixed point fractions. What else did we do? We did 2's complement representation, which helped us with the arithmetic. So we covered all of that in number systems. Now, a few key things over here. Well, I'll talk about the key things later on. Let's move on with our list of topics. The next one was digital circuits. This is where we talked about noise margin, fan in, fan out. How do you implement logic functions using CMOS MOS circuits, right? So that's what we looked at next. Then came our Boolean algebra, very key concept for the class. So basic Boolean algebra operations, laws and theorems, De Morgan's law, standard representations. We learned how to simplify Boolean expressions. We learned how to manipulate them to force some terms go to zero, combining things, duplicating terms to combine more. Those are all included in Boolean algebra. And then we said, all right, we need a more systematic way to do this logic minimization, which is why we started doing Karnaugh maps, Kmaps. Next, in Kmaps, we did what? 2, 3, 4, 5 until 5 variable Kmap. That's what we did over there. And most of you demonstrated a very good understanding of Kmaps in your exam. Next, in terms of combinational circuits, we talked about programming logic device, decoders and encoders, tri-state devices, multiplexers and demultiplexers, parity circuits, comparators, and adders. Next, we moved on to sequential circuits in the class. We started off with a simple latch. We built a flip-flop on top of a latch, which was an edge-sensitive sequential component. We looked at characteristic equations for JK, DT flip-flop, and then we also learned how to convert between different flip-flops. And then we started designing some complex circuits like shift register and a counter. Later on, I think this is where we had our second exam. After the second exam, we looked at how do you design counters using flip-flops. Any flip-flop, any counter, so with an arbitrary counting sequence. One of the later topics was finite state machines. We learned what are the concepts for Mealy finite state machine, Moore finite state machine, and we looked at mainly two main aspects of finite state machines. One was analysis. So given a circuit, finite state machine circuit, can you tell me what it is doing? Meaning, given a circuit, can you go to, so here, it is the reverse of this, right? So in the design, you give me a description. From that description, which essentially means a few sentences, I will write some assumptions, reasonable assumptions, and come up with a state transition diagram. From the state transition diagram, I will sketch out a symbolic state table, then I will do a state encoded state table, then I will choose a flip-flop, and I will draw the digital circuit at the end. So that was the design of the finite state machine, going from the description to the digital circuit. Analysis is exactly the reverse. Given the digital circuit, which involves logic gates and flip-flops, can I use the characteristic equations of the flip-flops and the logic expressions of the gates to go from the digital circuit back to the state transition diagram? That is reverse engineering, and it is certainly true for me, and I hope it is true for you too. Analysis is much easier than the design, because in the design process, going from the description to the state transition diagram, it can be tricky. right? So you will have to come up with an arbitrary assignment of the states. You have to, that's where your creativity comes in, right? You will have to think about some reasonable assumptions that you need to make, whether you are going for a Moore design or a Mealy design. But once you get to the state transition table, after that it's all very straightforward, right? But getting from the description to the state transition diagram, that is the crucial part. So for example, when we were doing a string recognizer, we were doing like a 010, recognize this particular string, and whenever you recognize this string, make the output a 1, right? So the description will just be those sentences, but you would take those statements and add some of your own assumptions as long as they are reasonable, and then come up with a state transition diagram. But once you come up with the state transition diagram, after that is just the same process. Pick a flip-flop, use the state tables of that particular flip-flop. Well, in that case, you would have to use the excitation tables of those flip-flops. So for the finite state machines, think of it as two main aspects: analysis and design. For analysis, you are using characteristic equations of the flip-flops and logic expressions of the gates. For the design process, the crucial thing is to go from a description or problem statement to the state transition diagram. All right. Next, we looked at memory and computer organization. So for memory, we looked at the static RAM, the 6 transistor structure, dynamic RAM, the 1 transistor and 1 capacitor structure, and why we need a refresh cycle for a dynamic RAM. Then as long as the as far as the ROM is concerned, which is a non-volatile memory, we looked at how ROM is essentially a combinational logic circuit. So you give me an address, I will tell you what is at that address. So there is an input, there is an output. So we can treat that as a combinational logic function. We looked at a diode-based RAM, a MOS-based RAM, a NOR structure, and a NAND structure for ROMs. The last thing that we looked at was the basic computer organization, in which we looked at the 5 steps that constitute an instruction cycle, register transfer notation, and some basic registers, for example, the program counter, instruction register, and the accumulator. So that's as far as what we did in the course. Now, coming to the format of the exam, it is going to be very similar to exam 1 and 2, which means there are going to be around 5 free response questions, and some of them may have sub questions, right? Some parts. Now, I want to use some time to talk about what you should definitely expect in terms of questions on the exam. Let's see, because this is it's been a long journey, and online classes are not something none of us signed up for online classes. So I want to give you guys I want you guys to focus your time and energy onto core ideas of the class and not get distracted with the overwhelming amount of information that is around it. Let's see. 1. These are the questions or ideas that you should definitely expect, right? 1 is design an arbitrary counter. Arbitrary counter. Now, what does that mean? That means you would have to I'm going to give you a sequence, and that sequence could be 0, 1, 3, 4, 0, 1, 3, 4, etc. Right? Some arbitrary 3-bit or a 4-bit counter for which you would have to design it, which means you would have to come up with either I will give you the flip-flop, or you may be asked to choose a flip-flop. So please read the question. If you are being asked to pick a flip-flop, or I'm giving you the flip-flop that I want you to use. If you were given the choice to use, what would you pick? D? What? All right. I would pick T. Everybody says D. All right. D might be easier so D might be initially easy, but remember at the end it will give you trouble, right? Okay. All right. Fine. Guys, be careful a little bit. All right. D will give you an easy next state table, and the excitation tables are easy. However, after that, the step is for Kmaps and then drawing the logic functions. That might be complex. So just keep that in mind. T for counters in general is easier, right? So I would prefer T, but all right, it's good to know that you guys like D as well. All right, so next let's move on. Design an arbitrary counter, and as you can see here, there are many skipped states, right? So how do you deal with that? How do you deal with skipped states? Meaning, if your counter randomly powers up in say state 5, right, which is not included in that sequence, what happens then, right? That's what happens then. Does it go to 4? Does it go to 0? So once you design it, once you complete the step of designing the counter, then for that particular design, this answer will be fixed. What happens will be fixed. So if it powers up in a random state like 5, what would happen? Would it come into the counting sequence? Would it never come into the counting sequence? Many answers are possible here. And the only way to figure that out is because you put don't cares. A lot of don't cares will be available here. Certainly for the states that you skipped over. Those don't cares, after you implement, meaning after you combine the ones and zeros, or sorry, if you're doing a SOP, you combine the ones. So after you combine the ones in your Kmap, you would treat those don't cares as either ones or zeros. So the implementation is fixed. So you should be able to answer what would happen if your counter randomly powers up in one of those skipped states. We have done a very exhaustive example of this when we were talking about counter design. So please go and rewatch that video. That'll help you a lot. So that is a question you should definitely expect. Questions here? Next question that you should definitely expect. 2. FSM analysis. So you will be given a circuit diagram. So it will have some flip-flops, it will have some logic gates. It may also have some combinational elements. So for example, it may have mux, it may have decoders, and you would have to use the characteristic equations of the flip-flops, or the logic expressions of the logic gates, or the logic expressions for the combinational components. For example, for mux, what is how are the outputs of a mux related to the inputs? How are the outputs of the decoder related to the inputs? So for all of that, you would need logic expressions or characteristic equations. We did a few examples of FSMS analysis, and that is something that you should expect. Given a circuit diagram, can you reach? So your end result should be a state diagram, or depending on how much time I have for the exam, I may ask you to stop one step earlier, state table, maybe state symbolic table, right? So if I feel like there is enough time, I may ask you to draw the state diagram, or I may ask you to simply stop at the state symbolic table. Questions here? Again, for these, for the FSM analysis, we called it reverse engineering. We did a few examples. I think we looked at JK, D flip-flop, T flip-flop. Many logic gates were involved. I think we looked at one example in which we had a 8-to-1 mux and multiple 2-to-4 decoders as well. So we looked at a few examples there. The only difficulty in this is you will have to be really careful tracking out your Boolean algebra, right? Because you're using Boolean algebra to relate all the inputs and outputs, whether the inputs are going into the flip-flops. So you would have to follow Boolean algebra to do this, because at each point in your circuit, there is a logic expressions. So you will have to be careful with the Boolean algebra that you use to do this. Questions here? Okay. Next question you should definitely expect. FSM design. So this is exactly the opposite, right? Like you will be given a problem statement. Design a string recognizer for 0, 1, 0, right? Every time you see a 0, 1, 0, make the output a 1, for example. I'm just giving you an example, but that's what I mean by problem statement. A few statements that denote the behavior of the desired state machine. And I may just give you which FSM to pick, right? I may say choose the FSM type of Moore or Mealy, and then design your FSM that does whatever is specified in the problem statement, but you have to pick. You have to use say a Moore machine or a Mealy machine. Now, in the FSM design, what is your end goal, right? So problem statement is the first step. Your last step would be to essentially draw out the FSM, right? So this might involve flip-flops, of course, logic gates, and etc. Now, depending on, again, the time allotment for problems, I may ask you to stop a little bit before that as well. So keep a look at the question. What do I want your last step of that FSM design to be? Do I want that to be like a final drawn circuit, or do I want that to be simply a state diagram, state transition diagram? Which means take the problem statement, make assumptions, reasonable assumptions, state those assumptions, draw out a state transition diagram which has all the like circles to denote states and arrows to indicate transitions, right? So I may ask you to stop there. So one problem on FSM design, one problem on FSM analysis, and one problem on an arbitrary counter design problem with skipped states. Questions so far? All right. Next, you should, this is 4, right? From the number systems, I'm going to expect you guys to know 2's complement representation, range of 2C numbers, overflow, how to detect overflow in 2's complement arithmetic. So here, focus on representing integer and fixed point numbers. I should say signed and unsigned. Well, 2's complement. So signed numbers in 2C format, right? How do you represent that? And then carry out, I shouldn't say carry out, I should say perform, because carry out is also a thing, right? So perform addition / subtraction using 2C numbers, detect overflow. So for your number systems, I would ask you guys to focus on these key ideas, but how I may throw in some conversions in there. So for example, I wouldn't expect you guys to, spend a lot of time doing conversions, because, we already tested that in exam 1, and it is basically a calculation exercise, not as much as a conceptual problem. So let's see. The number systems that you should absolutely be comfortable with are, of course, binary, hex, octal, and decimal. You guys should be able to go between one of these to the other quite comfortably and quickly. Questions here? All right. Next. Of course, you are going to see Kmaps, and I'm going to test these ideas. One is SOP, the other is POS. So combining zeros versus combining ones. How do you deal with don't cares? So for the final exam, because we have already tested 5 variable Kmap, for the final exam, I would not go as far as 5 variable Kmap. I will expect you guys to be comfortable with 4 variable Kmaps. So 4 variable Kmaps, how do you get the simplest SOP? How do you get the simplest POS? And how do you deal with don't care situations? And on the same slide, I'm going to go 6. 6 is logic representation. How do you represent logic? Right? We said, okay, you can represent logic using a schematic diagram, right? And then we said logic expressions. And then we said VHDL code. Then we said timing diagram. Then we said Venn diagrams. And we said statements. right? If this is true and that is true and then that is false, right? You could describe a logic using statements. What else? Do you guys remember anything else we did? Oh, truth tables. I forgot truth tables. How else can I represent logic? Yeah, nothing else is coming to mind right now. Okay, so the point of problem 6 here is, can you go comfortably between one to the other, right? Can you manipulate Venn diagrams and go to logic expressions? Can you go take truth tables and go to a schematic diagram? Can you take timing diagrams and go to some statements? So you going one to the other, right? Yeah, so transistors too, yes. So transistors are kind of like an extension to this, but yeah, you're right. Using transistors also, I can describe logic. Okay, so that's 6. Let me glance the topics here to see if I get more ideas. Okay, I can do that. Let's see. All right, so go all the way here. So Boolean algebra, your Boolean algebra properties, I may not give you a specific problem just to do Boolean algebra, but I'm going to assign you Boolean algebra work in the FSM analysis, right? So Boolean algebra is covered over there. We covered this, add here. So in terms of memory, given a ROM structure, can you tell me what the size is? Can you tell me what is stored in the ROM? So essentially, can you tell me at each address location, what is the data stored at that location, given a memory, given a ROM structure? So for example, this ROM structure could be NAND, NOR, it could be a diode based ROM, it could be a MOS transistor based ROM. But for a given ROM structure, I would expect you guys to know, how do I find the size of the ROM and how would you find out what is stored in that particular ROM? So if there are, say, 8 addresses, can you tell me what is stored at each address location in terms of what is the data stored at that each location? Next, in terms of the last lecture, the basic computer organization, I'm not going to test too much here because it's one of the recent lectures and I've not given you enough time to process this. So for basic computer organization, I'm simply going to test probably the functionality of what would you use a program counter, what would you use IC for, what would you use accumulator for. Very simple ideas. Something like the number of maximum operations. That's kind of exercise we did in today, number of max operations. So nothing too crucial with basic computer organization. Some simple things. Let's see. All right, and then I can perhaps add one last thing here, which is to synthesize logic functions using NAND/NOR mux decoder. That is it. So I think that that wraps up the most important ideas of the class, and I think I've given you guys the problems more or less. So now you know the exam, what the exam is going to be about. Um, so at this point, I can take your questions. All right. Let me stop recording here and talk to you guys a little bit.